Okay, so let's start with the data pre-processing. Look at this practical case of using medical image classification using machine learning. So actually, I will split it in some steps like this. For example, data acquisition, data description, taking data from Kaggle repository, and then also data pre-processing, resizing, grayscaling, and so on, and then feature extraction and so on. So I just took a random example that was done in the past and up to evaluation. So let's try to see from my PC. I don't know if it's necessary to run it again, but we can first of all look at it. Okay, so one thing I want to insist on is that my practical case study focuses only on GLCM feature extraction, GLCM feature extraction, and also you can have this. I mentioned the assignment, the radiomics feature. Yeah, it's very important to get, whenever you want to do machine learning, it's important to know this library to understand all the various features that you can have. For example, you have first order statistic feature, you have shape-based features, and so on. Yeah, like this. You see here we have 19, 16, 10, and so on. Yeah, this is the gray level covariance matrix for texture. So I want to use it for texture analysis in this case. Yeah. So this library is very important. And I will just try to go there very fast. And let's see how it happens. I will just take an example. Like energy. GLCM energy. Contrast. Just show it. So, okay, let me take just a contrast, for example, contrast, the 6. So, for example, here we said the constant is defined that the constant measures the local intensity variation when values away from the diagonal. That's in the case that I equals to j, the diagonal. So a larger value correlates with a greater disparity in intensity value among neighborhood pixels or voxels, for example. So this is how it's being computed. But advantage is that if you go to Python, you don't need this because a library that's existing that will help you to extract this kind of feature. So let me go there. I just want to use GLCM for malaria classification. So malaria classification, you get the data set on Kaggle repository. You can have it there. Yeah. So you just like malaria cell images. You have a kind of 27,000 images. So small, but I use just small part for exercise, and then I don't know if you know about some of these libraries. It's always important to start by importing some of them. NumPy for numerical calculation, Matplot for plotting. The globe to access the you have the CV2, OS, Cbon, Pandas, and so on, for example. So each time you want to use a function, it belongs, I think, from undergrad, you see the function belongs to a certain class. Like, for example, here, this class is important for us because we use GLCM, so we have to use the gray covariant matrix and the gray copox classes. Those are very important more than others because this is what we use. Yeah, so I collected my data here, so I kept it here. I can also show you sample of the data. So in this data, it was fixed already to be tested and trained, and then for training, you have two classes here, paratized and uninfected image, cell images, just a sample. Yeah, so in this case, you can see that this image is straight forward. You can see some dots there showing that it's therefore infected images. You can see all the way. At least you have a dot there. And if you notice, the images are of different sizes. Just varying. Some are big, some are small, and so on. So, yeah, when the images are already different, it's sometimes good to standardize the image size. This is one of the pre-processing. And also, this one, they have nothing. They have nothing. They are just, most of them, they have nothing. Not like the paratized. This is uninfected. Yeah. And you see that this data already, they belong to a folder with a label. So all these images are infected images. This one. And these images are uninfected. This is why I will use classical supervised machine learning. Why supervised? Because the data that I'm having is labeled. Here we have two labels, infected and uninfected. For example, here I want to set the size of the image to 128 because this image is in 2 dimensions, so 128 by 128. So I will fix it down. So the normal size is 128. So if I kind of import the data, then I will put the size because you saw the size were different, always changing. So it's good to standardize to one image size. Okay, what do I do? Now I've collected the image from I've done image acquisition. What I need to do now is to do the representation. I can't process images directly, sure, so I have to put them into some kind of array, array structure. Yeah, I have to keep them there. Yeah. So I need to keep in 2 weeks. I need to keep the trained images and the trained labels. I do same for the test images and test labels. Yeah. So what do? I just declare some empty arrays, and I will take, because each image has pixel representation, Yeah, it has a pixel representation. So I will keep the matrix of that image here in this array. I don't keep the photo. What do you see? I keep those values. So I will go into this data, the trained data. I try to take all the files in the trained data, and what I do is that each time I take them, I will read them and then I'll also resize. So this is a resize operation here. So resizing means I take the image and I set it to this size. It's 128 by 128, and I can add it to this empty array pile, append it. Yeah. So you can use a for loop to do for many images. And when you do that, you can check the shape of this, of what you've obtained. If you look at this, in my training set here, I have 500 items. Can you see 500 here? Yeah, training set for this class 500, and for this class 500. So it makes a total of 1,000. That is why this image is a 128 by 128, and there are 1,000 items like this. So the shape of this array, it gives 1,000 times the 128 by 128 image. It was standardized. Yeah. So here, one of the operations we did was just image resizing at this level. So we do same here for the testing. So the testing, we have 120 images, 128, 128 equally. And then what happens now? The labels that you had, our labels were paratized, parasitized, and uninfected. Yeah, but computer doesn't work that way. It has to be 0 or 1. So you have to do label encoding. So I think in all your machine learning you use, for example, categorical to numerical. Yeah, this library helps to do the same. So how do you change from text variable? Like if you want to manipulate the sex, somebody's sex is male or female, you can put 0 for male and female 1 or something like that. So you need to change it categorical. And when you do, you have to use this kind of label encoders. Yeah. So these images I will give this label, and those other images I will give this label. So in this case, we do a label for encoding. We encode the labels for the testing set and for the training set. And like for example, I display for the training set. You will see that I have 1,000, and in the 1,000 I have 500 0, which stands for, it has changed already. So my training set is no more the name of that folder. It's now parasitized now, which is 0. And then I have uninfected, which is 1. So I've changed them now. So you see I have 1,500 and 500. So once you do that, one of the things you need to do is like, you have to always divide your data set. So it's like this. This is 100%. So you need to do something like this always. So it depends on you. You can try. So most often you can do this. So you do like this. This is a whole data set. You can set 80% for training and 20% for testing. But in this case, the data came already for training and testing. So what I'm trying to do is that I will not have to split this set for 20 and 30, but I'll have to assign each set to the parts that I will use. That is why, in this case, I try to put these train images, I will assign it here as X train, yeah. And then the train labels, I will put it here, as you can see, and the same for the test set also. So I put the values that I extracted from the images here, and I also put the labels in the other one. So in this, you can now check how are these things looking like. It's always important to query the shape to know if actually it has some effect. Because it's normal, yeah, if you look at the shape for the training set, it has to be a 128 by 128 image, 1,000 that we use. That is why the shape is here. You can see that for the shape of this one is here. But this one is just a label. It's 0 or 1, so you have it 1,000 times. So you always check the shape, and if you do some things, it's a way to troubleshoot. Because if you don't check the shape, sometimes they may complain about the shape of the array or something. Maybe you think you are in maybe a binary or something where you have just one parameter. So it's good to check the shape. Okay, what do I do at this point? Now I want to define the extractor, DLCM extractor. Yeah. DLCM has a way of working. It works like this. In DLCM, you use two parameters to extract a feature. One of the parameters is theta, which is the angle that you use for extraction. Another parameter is the distance, the interpixel distance. And the interpixel distance can go up to 5. And the angles are well defined, and the normal angles. So this theta always belongs to 0, pi on 4, pi on 2, and 3 pi on 4. Yeah. You know this set? Yeah. So, and distance is any value that varies from 0 to something, but most often they use maximum of 5, the interpixel distance, to make sure that we have consistent. As I told you, if you extract many values, it doesn't mean you will use them all, because sometimes you have to choose. So you can decide to do combination. For example, in DLCM, there are many features. So in this case, I use how many features? I want to define this defining a feature extraction method. So for this one, you see, there is energy here, there is correlation, dissimilarity, homogeneity, and construct. So we have how many? 1, 2, 3, 4, 5. I choose among all the DLCM features just 5. I can show you that if you go to DLCM, you see that there are 24 features that you can extract. But among the 24 features, I choose just 5. And in the 5 features, I want to start extraction. 5 features doesn't mean I extract just 5. Look at what I will do. What I'm saying is all these features has 2 properties. One of the properties is the angle on which you are taking the angle and the distance between the 2 pixels, the interpixel distance. So I will start combining. Yeah, for the distance, I said you can choose any integer from 0. It's recommended not to go above 7. Yeah, and then for the angle, you can choose any angle here, from 0 to 3 pi on 4, for example. So you can also use pi 180, for example. So you have like 4 options and so on. Now, what do? I want to start extraction. So it's a computation. I want a property from this image. I will start the first combination. In the first combination, I will find the gray comatrix for the distance 1 and the angle 0. For distance 1 and angle 0, I will perform the GLCM. So if I perform the GLCM, in GLCM, I want to perform just 5 things out of 24. I choose just 5. So I will calculate the energy. So I'm looking for energy, which is here, this energy feature. I'll look for correlation, dissimilarity, homogeneity, constant. So this is what I use to extract bird. I will save it with these names. Okay? Yeah, I will save it with these names now. So this one will give me how many features? It gives 5 features. And it's only one combination, which is distance 1 and angle 0. Next, I go for distance 3, angle 0. I do 5 again. 5 extraction. Again, I go for distance 5 and angle still 0. I didn't change the angle, I'm still there. And after I go for distance 0, I go for pi on 4. So I'm using pi on 4, this one. Yeah. So I'm extracting, and that's how you can extract. You can automate just in one block. It's because it's just some practice. It's possible to automate these things. Just one block, you use a for loop to automate the extraction. So in this case, I'm calculating 5 how many times? 1 time, 2 times, 3 times, 4 times, 5 times, and 6 times. So I have until GLCM 6. And each time I extract them, I have to save in a pandas data frame, in this data frame. And exactly I have this. You notice already. This is a normal data frame that you have. Because with this data frame, you can now perform all the other things. So I've extracted here for 1,000 images, I've extracted 30 features per images. And then it gives this. So I have, and these are the names here. Yeah, these are the names. This is for machine learning. In deep learning, it doesn't work this way. Yeah, for machine learning, we do like this. You can do LBP, you can do a morphological feature extraction, find the area, the perimeter, and so on. You always find like this. So in the assignment, I asked to extract at least 150 features. You see that only for GLCM, if you focus on maybe 8 features or 5, because we did 5 here, we can focus on more, maybe 8 features, and then we try to do combination. Only with GLCM, you can extract more than 100 features, more than maybe 150 features. But are they relevant? You need to do selection in that case. But here we have just 30. So I didn't process with feature selection, though we know that we can use feature selection for elimination. So we have the extractor here, and this is the extracted features, for example. And when the features are extracted, you can see the same thing for the test. Yeah. Why do we do for the test? Because we have to put the train and test data on the same standard to be sure to run the testing. If they are different, you cannot check how the model works. I want to explain how you use the test data set. This 20%. This one, this test data set. You have 80% here for training. The testing is here. So the testing is still a pandas framework. Yes. Test original has these values. So it has something like this and something like this. It's how many? Maybe I think it was 60 for one. So we have 60 values like this with 0, 1, 0, 1 according to the prediction. Now I will do some prediction. It means once my model is done, I will do the prediction, and the prediction will tell me exactly. It will tell me this is 0, this is 0, this is 0, this is 1, 0, and 1. You can see that here there is correct classification. Here is also correct, but here it's not. Because this image was labeled as 1, but it predicted 0. So we use this data set and the prediction to check how efficient is our model. Because there's a prediction here and there's a test here. So this test, we have it already. We have it 20%. How do we use it? We will do prediction. And when we do prediction using the model, we compare these two to get accuracy and so on. So let's start by training the machine learning. So here we have one more thing. Here we just GLCM. So we concatenated. You can see it here. There's some kind of concatenation you can see here. Concatenation means I've extracted some features and I'm adding and adding and adding. It means if you use for assignment, you are asked to use many feature extractors. Like you use some other morphological, you have to add those ones also. But one thing remains clear is that you must have 1,000 feature extracted. That is why this shape is very important. Somewhere here. Then if you have 1,000 images, you must have 1,000 here. And then if you have 30 features, it's 30 columns. If you have 100 features, you 100. So you have to concatenate. And if you concatenate, you extract maybe 900 and 1,000, you will not go. And you need to make it same. So you use this feature extraction to extract many. You can use many techniques to have features, and you need to do concatenation, like joining them together. And if you join now, you have a set that you can use for training and testing. In our case, it was splitted already in the beginning. But in most cases, when you have this that you have to split. It's simple to split. You just find the code online to split into training and testing, put the proportion. Yeah. So we've also tried to see. So in this case, what do? We use that training set to train the model. So we give him the values and the labels, and then we do. It's simple this time. So you see, you have, for example, the C coefficient here, that's 1, and the kernel here is linear. There's a linear kernel. And then there are many, you can check on the documentation of support vector, you will see there are many other hyperparameters that you can use to alter. And then because as you are doing, it will change. For this kind of training, we just quickly try to show the accuracy. At least show that the training is finished and we can see the accuracy. Yeah. So like in this case, you can, how do you evaluate the accuracy? As I said, you must try to know the predicted results from the test set. You have to compare them. What I predicted and what I had as always, because you cannot see something and say this is not good. You must check it somewhere. So the test set is where I check and the prediction. I compare. So the test set and the prediction are used for evaluation. And from there it's easy to get the accuracy. You see? That is why to get the accuracy, you must do the prediction and the testing, you must compare them. From there you can get true positive, true negative. You remember the formula for accuracy has a true positive and so on. This is where you get them. Because you check like this one, you will see this one is a true positive, but here is false alarm, for example. So all these things you have to consider. And once you do it, the first thing is that you can have the accuracy. Yeah. And then we do same for the decision tree. These are very basic classifiers. You can add hyperparameters here. It's requested in the assignment, and also You can have the accuracy, you have the random forest, for example. And then you have the linear discrimination analysis and the logistic regression. The function is a little old now. That's why you have this warning message. But it's performing best here. In terms of accuracy, at least you have 77.5%. Because it's 0.775, so 77.5%. So in terms of accuracy, this is the best now. From all the 5 supervised learning, state-of-the-art machine learning classifiers. So you think about, how can I increase the accuracy? Basically, you have to change those hyperparameters. You have to change some values and so on. You have to make sure that the pre-processing is good. You can increase the amount of data you use to train the model, for example. I use 5,000. The original data set is 27,000. You see that with 27,000 is more informative, so they have more information about these things. So now I will choose just one thing. So the model performance, I want to evaluate this model, and one of the things I just choose this model because it's the best, 77%. So the model performance here, it gives, so this is why I'm using the confusion matrix for logistic regression, because it was the best among classifiers. And now the confusion matrix, I want to display just like this to see. In this test data set, we have how many were correctly predicted and what were the false predictions like this. When you have this information, it's also important, true positive, true negative, true, and false negative and false positive. But at the end of the day, you ask yourself, like, another visualization can be different. Like you can do some this kind of visualization. You have the classes 0, 1, 1. You see the number of correct predicted cases and so on. Or you can try again this kind of visualization where you actually specify the classes. You have the paratized class and the uninfected classes, and you show exactly where they have the perfect classification or the misclassifications, for example. Once you have done that, the other matrices, you can use the classification report function to get them. So, like for example, the precision, we get formula for precision, recall, F1 score, and so on. You can just complete it this way and save the model. Save the model, you can reload, use, and test again and so on. So these are the kind of things you have to do. So if you have any question, please.